Let's study this protocol, which is often referenced as BB84 protocol, after the first letters of the names of its inventors. The protocol has multiple steps. On the first step, both Alice and Bob generate long enough random sequences of zeros and ones. To do this, they can use measurements of single photons polarized along the vector plus. If you send such photon to a vertically oriented polarizer, it passes with probability 1/2 and reflects with the same probability. So when the photon passes, we can assign this result the number 1, and when it reflects, number 0. This is one of many possible ways to generate a truly random bit. So Alice and Bob generate as many random bits as they want, say 10,000. Actually, Alice needs 2 random sequences of this length. Let's name them A1 and A2. And the random sequence of Bob we will name B1. Please note that random sequences of Alice and Bob are independent. Nobody except Alice has access to her random sequences, and so is with the Bob's sequence also. On the next step, Alice and Bob begin interaction. They choose a channel through which Alice can send photons to Bob. It is important that this channel does not alter the photon polarization. So Alice takes a bit from her random sequence A1, generated on the step 1. If this bit is 0, then she creates a photon polarized in the 0-1 basis. The polarization of this photon is defined by the corresponding bit of the sequence A2. If the bit from A2 sequence is 1, then she polarizes the photon vertically, otherwise horizontally. But if the bit in the sequence A1 is 1, then Alice creates a photon polarized in the Hadamard basis. Then, if the bit from A2 sequence is 1, then she polarizes photon along the vector plus. Otherwise, she polarizes it along vector minus. Good. Now, for each photon generated by Alice, it is random in 2 senses. First, its basis is random. Second, its value in this basis is also random. Each generated photon Alice sends to Bob via that communication channel. When Bob receives a photon from Alice, he does not know its polarization. So he takes 1 bit from his random sequence B1. If the bit is 0, then Bob measures the photon in the 0-1 basis. If the bit is 1, then Bob measures this photon in the Hadamard basis. Now, if the corresponding bits in the A1 and B1 sequences appear to be equal, then for the photon which was generated using this bit, Bob guesses the right measurement basis, and he obtains the correct bit for the sequence A2 generated by Alice. For those bits that differ in A1 and B1, Bob obtains completely random result for the measured bit. But at this step, Bob does not know which bits are correct and which are not, so he carefully saves all his measurement results. On the step 3, Alice calls Bob using some open and insecure communication channel, and she sends him her A1 sequence. The only requirement for this channel is that Alice and Bob must be sure that they are talking to each other and not to Eve. Eve may only eavesdrop this channel. Now, when Bob has A1 sequence, he knows which photons he measured in correct basis. He then returns Alice the numbers of photons which he measured correctly, but not the result of the measurement. After this step, both Alice and Bob share some bits from the A2 sequence, and they both know which bits these are. So now they have the shared secret key, composed of these bits. Now, all this would be unnecessary if there was no if. But if exists, and we suppose that she controls both channels. That what used for photons transfer and for afterwards conversation. What can if possibly do? First of all, if could intercept the photons sent by Alice. But there's no way if could intercept just a part of a photon. Photons are indivisible, so when if receives a photon, Bob receives nothing. And thus Alice and Bob will soon find out that some photons sent by Alice were lost. If this situation happens, they will agree that they have an intruder and the key was not generated. To avoid that, Eve, when she intercepts a photon, must send some photon to Bob, so Alice and Bob wouldn't notice her intrusion. The question is, what to send? If Eve could duplicate the photon, then she might send the exact copy of the photon she received. But it's not possible thanks to no cloning theorem. So the best thing she can do is to measure the photon and send Bob the same photon as she just measured. And the problem with that, as you might guess, is Eve doesn't know which basis to choose. She does not know the basis chosen by Alice to polarize the photon. And she does not know the basis that Bob will choose for his measurement. So let's count the odds. If for some photon Bob does not guess the basis chosen by Alice right, then on the step 3, this photon will be eliminated from consideration by Alice and Bob, no matter what Eve did with this photon. So we need to consider only the photons for which Alice and Bob have chosen the same basis. For each such situation, there are two possibilities. First, Eve guesses the basis correctly, and second, Eve chooses the incorrect basis. In the first case, which has the probability 1/2, Eve wins for this photon, and she has exactly the same random bit as Alice and Bob. In the second situation, the probability of which is also 1/2, Eve also can win if she randomly obtains the same bit encoded by Alice. The probability of this is 1/2, and Bob also randomly obtains the correct bit from the photon encoded by Eve. This is also 1/2. So the whole probability for Eve to invisibly intrude and obtain the correct bit is 1/2 plus 1/2 in the power 3, which is 5/8. Looks good for Eve. It is even bigger than 1/2. But Eve has this probability for each single bit. And as you remember, there are many bits in this transfer. In our example, there were 10,000 bits. And the probability to obtain every bit correctly becomes for Eve extremely small. It is like 5/8 in the power 5,000. This is the approximate number of bits for which Alice and Bob will have measurements in the same basis. So the next and final step of the algorithm is this. Alice and Bob now have some shared secret key, but they don't know yet if it is similar, because they don't know if Eve interfered or not. So they decide to randomly choose some bits of their shared key and compare them over the open insecure channel. This is the final check, which easily reveals the actions of Eve. The more bits Alice and Bob choose to check, the less is probability for Eve to be undetected. This probability is 5/8 in the power n, where n is the number of checks. With just 10 checks, the probability of Eve's detection becomes 99%. The bits that were chosen for this check are, of course, removed from the shared key. If Eve were detected, some bits of the shared key appear to be different at Alice and Bob, then Alice and Bob agree that the key was not generated, and they have to repeat the whole procedure again. But if the check has passed, then Alice and Bob can be sure that they now have an identical shared key, which nobody else has.